Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Counting independent sets up to the tree threshold.
Okay. So, like the title says, I'll be talking about independent sets. So let me just start with the quick definition of the model. So what we want is to count or sample weighted independent sets of a given graph G, and the weights are determined by an activity parameter lambda, so that the weight is of a given set is proportional to lambda to the raised to the size of the set. And for this talk, it will be convenient to think of the model as one where we have configurations which are binary assignments to the vertices of the graph. So a vertex could be either occupied or unoccupied. And since we're talking about independent sets, we only allow configurations in which we don't have two neighboring sites being occupied, and then each such configuration gets a weight as described here. And this is the model, for example, in statistical physics for a lattice gas, or it also comes up in communication networks. Just maybe a quick illustration for the lattice gas interpretation. So you can think of a very fine grid as some kind of approximation of space, and then you have some molecules with finite radius that can sit at the intersections. Then if you take the appropriate radius of the molecules, then you can see that you can have molecules everywhere, except that you cannot have two molecules on two neighboring vertices. Okay. So this is the model. What we'd like to do, at least the computational problem that we're interested is to give a very close approximation to the sum over independent sets of this weight. Basically count these weighted independent sets. It's called a partition function in statistical physics, or an equivalent computational problem is to approximately sample from the distribution where the weight of each independent set is proportional to what I wrote above. Okay. Now, intuitively, the problem becomes harder as the activity parameter grows. So one thing should be obvious, that as we increase lambda, we give more and more preference to the larger and the denser sets. So obviously, if we could sample with the lambda arbitrarily large, we would just find the maximum independent set, which is an NP-hard problem. And actually, we even know we can say things more precisely. In fact, it is known that it is NP-hard to approximate this sum even to within a polynomial factor. Even, for example, if you look only at graphs at maximum degree delta, already when the activity parameter is something that is inverse in the maximum degree. On the other hand, on the positive side, we also know that there exists a fully polynomial randomized approximation scheme, also for lambda, which is somewhat in the order that is inverse linear in the maximum degree. So this is the number that I wrote down here, and this is so here we have an algorithm for approximate counting or sampling that is based on the Glauber dynamics, which is a very simple Markov chain Monte Carlo algorithm, where basically in each step you just choose a random vertex and update its value to be occupied or unoccupied condition on the neighbors. And now this Markov chain is known to converge to the right distribution. The only question whether it does so in polynomial time or not. And the analysis done in this paper shows that, for example, what the best known up to this work is that for lambda at most 2 over delta minus 2, this Markov chain is guaranteed to mix rapidly for any graph of maximum degree delta. Now you may say, okay, so I know that it's more or less inverse linear, the game that we're playing at, but so why should we care any further? But actually we do want to know the exact constants here, because usually the graphs of interest are one with a small maximum degree, like a lattice, and we want to know exactly where is that threshold. Okay. Now I want slightly switch to a related problem, a combinatorial problem. So now I don't, this is no longer a computational problem. What I now want to investigate is the structure of the set of independent sets. And in particular, what I want to analyze are dependencies in distance. Namely, I want to see whether there is a correlation between the fact that a certain vertex is occupied and the configuration far from it. So for this talk, I will concentrate on a very specific definition, one that is essentially equivalent to what is called uniqueness of the Gibbs measure in statistical physics, but it is enough just to, I mean, the definition is just probabilistic. So basically, we say that the Gibbs measure is unique if the following holds. So we look at an arbitrary vertex, let's say V here, and I want to compare the probability that V is occupied under two different conditions. What are the conditions? So I look at all the vertices at distance L from V, and then I fix the vertices at distance L to two different conditions. Let's say one that maximizes the probability that V is occupied, and the other one, the one that minimizes that, and I look at the difference between the two probabilities. And this will be sort of the influence on V of the configuration at distance L. And the question is whether that influence goes to 0 with L or not. And if it does go to 0, then I say that the Gibbs measure is unique. So it's some kind of, you can think of that, some measure of decay of correlation, and whenever I say that the Gibbs measure is unique for some graph, this is what I mean. So as I wrote it down here, this definition makes sense for a specific infinite graph, but I can also think of it in a more sort of uniform way, something more similar to the way we think of computational complexity. So I want to ask this question on a general graph of degree delta. So what I want to ask here is, for what values of lambda can I take some decaying function with L, some function that goes to 0, such that for every graph of maximum degree delta, the influence of the configuration at distance L from a certain vertex is at most delta L. So that is that on any graph of maximum degree delta, this influence goes to 0. And so now I can also look at finite graphs. And this question is very related to the computational question I asked before, for which values of lambda is there an efficient approximation scheme. But let me just say what we know about this problem. So what we know is that there is indeed a unique measure of all graphs of maximum degree delta, again at the same threshold that we had before for the computational problem. And this is not, it's the same proof, sort of the same argument that shows that the Markov chain is rapidly mixing is based on some of contraction of the Markov operator. Also says that you can translate this contraction to a contraction sort of in space, sort of as you move away from V to get this kind of decay of correlation. So yeah, so it's the same bound, and it's a part of a more general and sometimes also direct relationships between the two notions, that in some cases you can go from one to the other and vice versa. And On the sort of bound in the other direction, so the only example that we have is the delta regular tree, where we know exactly the threshold for this kind of decay of correlations that I defined before. So we know there is some critical lambda, which is given here, and we know that the correlations as I defined before decay with distance if and only if lambda is at most this critical lambda, and above it they persist over distance.
Who is this?
This is, I think, the first one to find this threshold is Kelly. It's back in the 70s, I think. Yeah, it includes the equality. So if the inequality is strict, then the decay is exponential in distance. If it's equality, then it decays, but not exponentially. And so this has some algorithmic implications. And even though the tree by itself is easy, computationally is easy, you can always count the number of independent sets regardless of lambda in linear time, and even the Markov chain is always rapidly mixing. But there is, but just the fact that on the tree correlations do not decay with distance above this value means that any kind of argument that was used here for the computational problem, or the argument that established this bound for the computational problem, is bound to fail above lambda c, simply because this kind of argument automatically implies a sort of a decay of correlation in distance in any graph. So it cannot work above this critical value for the tree. Okay, so let's go on here. But actually it has been conjectured that this critical value is actually captures all graphs. So the tree is the worst case, at least in terms of the combinatorial problem. The tree is the worst case. So in fact, that for any graph, the correlation should decay with distance all the way up to this critical value. And one thing I want to say about this conjecture is that actually we don't have an interesting example where we know that it's true, so rigorously. So we know for some graphs we have some result-based simulations, but I don't think there is any non-trivial infinite graph where we can say that the critical value for that graph is above the tree. So this conjecture was made even though there are no sort of specific numerical evidence for it. For the Ising model with no external field, so whether do you know that this kind of conjecture is true?
Yes. That's the critical temperature.
So with no external field, it is true. I mean, I don't know if it was. I know how to prove it, but not by a different way than what I will do here. But I don't know if it was investigated.
Well, it's sort of slightly counterintuitive, right? You might say, if I have, for the Ising model, I have FKG,
Yeah.
so therefore my influence of the boundary should be stronger if I have loops, because I get the same information twice.
It's not so. So the conjecture is, for example, for Ising with no external field, it is true. And even for antiferromagnetic Ising, it's true, even with external field. But okay, so even though, so sort of what I wanted to say with the fact that there are no specific graphs for which we know this to be true is that solving this conjecture is also meaningful in the sense that it will provide new bounds for interesting graphs. And actually, and the conjecture is true. That's the sort of the context of this talk. And specifically, the main result here is the following. So fix any delta and lambda and look at the at a general graph of maximum degree delta, and again consider the influence of configurations at distance L on any arbitrary vertex V, then this influence, or sort of the difference between the maximizer and minimizer of the probability that V is occupied, is maximized by taking G to be the regular tree. And this is true for any L, so it's a finite statement. It's not just in the limit. Huh?
Say regular tree, do you mean at the root it has a degree delta minus 1 and delta everywhere else? Or do you mean
No, it has delta at the root too. Yeah. The root has delta neighbors too, degree delta too. So the root, yeah, it's what. Yeah, yeah. It's a regular graph. Yeah. Okay, so again, what the theorem says that if you look at sort of any particular graph, compare the difference between, let's say, these two configurations, then you might just as well replace it by the regular tree and you'll get a bigger difference. Put the conditions at level L below and you'll get a bigger difference. That is what the theorem says.
Now, in your graph, which is not yet a tree, so you only consider configurations which are extendable to the outside, or you just cut off the graph at radius R and consider the...
These are always the worst case. I'm not sure. I mean, I can consider any, basically...
So is it fair to think
Yes.
of all the leaves as having degree 1? So you cut the graph at this radius?
Yeah.
The rest of the graph doesn't change.
Yeah, but once you fix, if you fix all the vertices at some radius, then the rest of the graph has no role, just by the condition.
Probability zero.
Oh?
You cannot fix them to the sum, right? Maybe it's
That it's not in the...
configurations
Yes.
which don't extend, then potentially you have more configurations, and maybe these will have more influence. So it is meaningful, unless you're not but up.
So I don't... first of all, I don't think it should
But you allow
matter.
everything. You allow also configurations that do not extend, right? It's a finite statement.
Yes, but it's going to think. But so you're worried about the fact that some configurations are not realizable because it's independent sets, the hardcore constraint.
Yeah, that's right.
Well, I mean, actually not worried, because you say the
First of all-
is maximum degree delta,
Yeah.
and therefore you're allowed to erase the outside.
Yeah.
So if you prove that this
Yes.
theorem, I'm not worried.
Yeah.
at all.
Okay. And also, it's the fact that it's also true not just for hardcore constraint. I mean, so it's true in a more general sense. Okay. And so the immediate corollary is that indeed, for the combinatorial question that I asked before, we now know the threshold exactly. So for all graphs, we know that the Gibbs measure is unique if the activity is at most lambda c, and then above lambda c we already have an example of a graph which is not unique, which is just a regular tree.
Wait, for lambda equals lambda c,
Yes.
the uniqueness of the Gibbs measure
Yeah.
may be sort of tricky. It could be that for almost all boundary conditions, but not for all boundary conditions.
No, it's for all boundary conditions. So for the tree we know that it's for all boundary condition, and exactly what this theorem says is that, I mean, this is unique for...
At lambda c delta of L, we don't only know uniqueness of the Gibbs
It's
measure
a
in the
branching
traditional
constant.
sense, but even that the delta of L goes to.
Yes. Okay. And in terms of the algorithmic implications, so there is some general framework of translating the fact just that we know that the Gibbs measure is unique to sort of rapid mixing of the Markov chain that I described before, but this framework is somewhat limited in the sense that currently we only know that it holds the direct relationship in this direction holds in a certain class of graphs. For example, graphs with sub-exponential growth, meaning that the radius of balls grows sub-exponentially in the radius. The volume of balls go sub-exponentially with the radius. So for trees, I can massage it to work, because actually what really matters is the separators. This is just some way of capturing the fact that the separators are small. The exact actually way of phrasing it is that they have small separators. So this is sort of the standard thing we do in this field. We prove sort of decay of correlation and distance, and then deduce a rapid mixing of the Markov chain from that. But actually, the nice thing about this work is that the analysis yields a new algorithm, and now we no longer have the problem that it only works in a certain class of graph. So there is a new algorithm here that works for any lambda between the critical lambda, and it works for any graph, and furthermore it's a deterministic algorithm. So it gives, yes, I will. So basically it gives a 1/epsilon approximation of the independent set sum in time, which is polynomial in n and 1/epsilon. I mean, one small caveat here is that the degree of the polynomial depends on the degree, even though it's a mild dependence, but still it's. So strictly speaking, we get the fully polynomial approximation scheme only for graphs of fixed degree. But again, this is the interesting case usually. Before I go on to the proofs, I just want to mention a couple of specific interesting cases that sort of we get from this result. The first thing is I want to mention is the case of lambda equals 1, which is just the normal counting of independent sets. So we now also get that we have efficient approximate counting for graphs of maximum degree 5, where the previous bound was 4. And this probably closes a gap, because we believe this to be hard already for delta equals 6, or at least one thing we can say for delta equals 6 is that the Markov chain, there are graphs of maximum degree 6 for which the Markov chain takes exponential time to mix. And another point about this is that because the algorithm is deterministic, it's probably the first example of a fully polynomial approximation scheme for a natural sharp P-complete problem. And at least that's for the best of my knowledge. I heard just something I wasn't aware of, but some people brought my attention to that fact. So, for example, counting exactly the number of independent sets in graphs of maximum degree 4 is sharp P-complete, and by the results here, we have a deterministic approximation scheme for this problem.
So does that work towards proving that randomness doesn't help?
Yeah, but still, no. But there are some the volume right. The volume problem is there are some even approximation. Okay, and
So does that give new complexity?
just yeah. So from what I understood, you can always sort of cook up trivial examples where you would get approximation schemes, but this was the first one. Because so actually I got an email from some people who worked on proving that there isn't a deterministic approximation scheme, and then they heard about this paper, and they told me that I should mention this fact, because actually they were trying to give the first from a different program. Yeah. And the other specific example I want to mention is the square lattice, which is probably the graph that is most looked at in statistical physics. And So here by simulations, we believe there to be a critical activity at around 3.79, but the rigorous bounds are far from it. Actually, this I should probably sort of actually there is an update on this, but the best previous bound that I was aware of when I wrote the slides were this 125, which is works by relating the critical activity to the critical probability for side percolation, and this gives 1.25 if you put in the rigorous bound for the critical probability for side percolation, and 1.45 if you plug in what is believed to be the critical probability.
So this 1.25 is not 5/4.
No, no. And actually, since then, I also heard of a result that gives 1.5 roughly. It's a computer-assisted proof of just sort of computing the Bruching-Schlossman condition, if you know what that is. But so that gives 1 point. It was a thesis of someone from a few years ago, and that gives 1.5. But in any case, the bound that we get from the tree beats all that and gives 1.69.
Something about working or not working with belief propagation
So the lattice propagation is just calculating the same thing as the tree. So if you have a regular
You approximate by a tree.
then the question is to know exactly what you're going to do, but the only question is how close is the tree to that. And this doesn't say.
So so now I'm more or less done with the background, and I'm ready to go to the proofs. So any questions before I go? Okay. So we switch to the proof. So here's the main theorem again, saying that we can always go from a general graph to a tree and only increase the influence of conditions at distance L. And actually, the first part of the theorem is to prove it when G is just a general tree, just not necessarily regular. And even that was not known before. And the reason it's not so trivial is that there are all sorts of non-monotone phenomena, even on trees, especially irregular trees. But nevertheless, it's true. I will not go into that. I think the more interesting part is comparing a general graph to a tree. But just want to say that, okay, so from the first part, we can now just compare G to any tree of just maximum degree D, not necessarily regular. This is all I want from this part. Okay. So now I move on to give a sort of true representation for general graphs. So actually the way I'm going to prove the theorem is I will say that if you start from a graph G and some vertex V in G, I can always give you a tree, which is a function of the graph and the vertex I'm looking at, which will have the same maximum degree and will actually, for what I'm interested in, will represent exactly G and V, namely the probability that V is occupied in G will be exactly the same as the probability that the root is occupied in the tree that I get. But of course, this is by itself is not enough. There's I have to do it in some uniform way. And indeed, the full sort of statement here is that I will use the same tree even when I put conditions on G. So so I just look now at conditional probabilities. So I look at I look at some configuration, let's say a distance L from V, and I look what is the probability that V is occupied in G condition on that configuration. Then it's exactly the same as the probability that the root of this tree is occupied, condition on, there is a corresponding condition on the tree, which also will be a distance L from the root. That's the important part here.
And so you're
And
saying that are a set of spins on which you could put that are a set of sites.
Yeah, so I start from a set of sites and spins fixed here, and I get some set of sites and spins fixed here. The distance, the important thing here is that the distance is the same, or at least in the distance in the tree is at least what it was in G. And another important thing is that the tree is the same for all these conditions.
Right.
So yeah, okay, that's the important part here. Okay. So once I have something like that, then obviously I can prove the main theorem, because when I want to compare two conditions on G, I just go and compare them on the tree. Okay. So the next thing I want to do is just describe the construction of this tree. So this tree is essentially a tree of self-avoiding walks with some minor corrections. So basically, as a tree of self-avoiding walks, you can just think of it as a tree of paths starting at the vertex that we are looking at. So let me just illustrate. So I put in here a small example of a graph and the corresponding tree. So I said tree of paths. So the root just corresponds to the path of length 0, which is just the vertex itself. And then children of a vertex in the tree just correspond to continuation of the path. So for example, from A I can go to B, so I have this child in the tree, and notice that now I'm stuck, I cannot go anywhere, so B is a leaf in the tree. On the other hand, if I go to C, I get another vertex, but now I can continue, so there is another, so C has another child here. And now some interesting things happen when I close loops. So what happened when I close loop? So for example, here I close a loop that started at A and ended at A. So I do add the vertex that closed the loop, but I fix it to be either occupied or unoccupied.
Or the root.
So, okay. So whenever I close a loop, so for example, in this case, I close the loop, I add the vertex to the tree, but it's a fixed vertex. It's fixed to be either occupied or unoccupied according to the following binary rule. So in order to describe I need to have an ordering on the neighbors of each vertex, and then depending on whether the edge that closing the cycle is larger than the one that started it, that's the binary rule. If it's larger, then it's occupied. If it's smaller, it's going to be unoccupied. Okay, so for example here, if I just take the lexicographic order, then I closed the cycle with an edge coming from D, and I started it with C, so D is larger than C, and I decide to be occupied.
Wait, why did you start this? How you start?
This cycle was A, C, D, A. Yeah. Okay. For example, will always be the reverse cycle. I think it's here, and then it will be unoccupied. Let's just maybe smile.
So you just asked whether on the last edge the two elements are ordered in one dimension.
No, what I do is compare the last edge to the first edge. So, and I don't. So what I compare is the neighbors that I went to in the first step and the neighbor that I came from in the last step. Okay. And so for just maybe more examples. So from D here I can also continue to F, and then to E, and then close the cycle at D. And then again, I fix it in this case to be unoccupied because I closed the cycle coming from E and I started from F. Okay, so this is the construction of the tree. Now I still have to tell you how I copy conditions from G to the tree, and actually this is a very natural correspondence. It's what you would expect. Namely, you see here that every vertex in the tree, you can think of it as being a copy of some vertex in G, namely the vertex that was visited when I created this vertex in the tree. So if, for example, I want to put a condition that C is unoccupied, the corresponding condition on the tree is just that all copies of C are unoccupied.
Is it clear that, oh wait, the sites that you say are occupied or unoccupied from your choice are not sites that were in the tree to begin with?
Yeah, okay, so
I mean,
you're afraid there will be some contradictions here, but they were correct. Okay, so let me just finish this description and I will say why this is not a problem. Okay, but just to see, so if I want to condition on C being unoccupied, I just have all the copies of C unoccupied. And similarly, for example, if I want E to be occupied, I just copy take all the copies of E to be occupied. Now, to your question, the thing about the tree is that you only need to look at the sort of the first condition that you encounter coming down, because everything below it has, in terms of conditional probability, has no influence on the root. That's sort of an intuitive explanation. But the right explanation is why you can actually erase this thing below the first occurrence of any condition, is that I'm slightly cheating in it. The right construction of the tree is to first put the condition and then construct the tree of paths. And whenever
But
you
then you
have
to argue that
yeah, but that doesn't
that you
change.
get the
Yeah,
same thing
yeah,
with any
okay.
condition that you put on.
I do, because I get exactly that. But
Right.
so you should. I mean, what comes in the proof is that you first put the condition, and now you construct the tree of paths, and whenever you get to a fixed vertex, you don't continue any further. That's really the correct construction of the tree. But
And you're going to tell us that gives the same.
yeah, well, because this is exactly so it's exactly the same as doing what I did here and erasing everything below the first condition.
Now, I noted in particular that
Yeah.
you didn't label the end vertices of your loops.
That's what I'm
Yeah,
saying.
because it's not so.
If you did, then you might create a contradiction.
Well, actually not, because the thing is that if there is an occurrence here, then there's always an occurrence above it of some ancestor, and you will already fix the ancestor. So you're saying, suppose this is a copy of A. Suppose I want to fix A to something.
Right.
But the thing is that fixing A to something will mean that there is an ancestor that is already fixed, and then everything below that ancestor is irrelevant. So you never get to this contradiction.
And
Okay.
so you will not create.
If you think of it in the way that I described, that you first put the condition and then construct the tree of path, then you will never get the
What if
contradiction.
you put non-permitted, if you condition on the event of probability here, in the original graph? Well, you see, I could in
yes.
the original graph, I can't really consider it as conditioning in the probability sense, but I could sort of just say,
Yeah.
I can occupy two neighbors, and I can just still
Yeah.
integrate over all.
Yeah,
where
but
I
you will get a condition on the tree again, and the
but
thing
it
is,
works even in that case.
yes, because this correspondence, again, like I said before, also works for Ising model, for example. There's nothing. I'm only using the fact that there are only two spins. This is the only thing I'm using for this, and you will see it also in the proof.
So that the edges they could have zero weights or not. You don't get.
Yeah.
They could be negative.
Yeah. Okay. Okay, so just to finish here again, so if now I want to compare what happens when I change the configuration on the same vertices, all I have to do is change the configuration on the trees. So that's why I get the main theorem. So let me move on.
Wait, no, I don't quite understand
Yeah.
yet. Why is the probability distribution the same?
Which one? No, this is what I'm going to prove. I haven't
Oh, I
proved.
see. I thought you have already.
No, no. Okay, so, okay. So the way I'm going to prove this the fact that the two probabilities are the same, is by describing a procedure to calculate the probability that V is occupied in a general graph. Okay, and this procedure will do exactly the same calculation as on the tree, and that's how we will get the equality. So now I want to start by describing these procedures. So I will start with some notation. It's more convenient to actually rather than look at the probability that V is occupied, to make a change of variable and look at the ratio of probability that it's occupied to not being occupied. It's just for convenience. So I have this notation R for this ratio, and then with the superscript and subscript indicating what are the parameters involved. Now I'm going to use a very basic rule here. So suppose we start from two separate graphs, G1 and G2, and suppose we already know what are the probability of occupation for V and U, and now I'm going to add an edge connecting V and U and the two graphs. And I want to ask what is the new probability of occupation at V, then there is a simple formula for that. Basically what it says is that the new ratio at V for the new graph G that I created is what it used to be, that's in G1, and then I have to factor in the influence that comes from U. Okay, and this is it's really, there's nothing to it. You just write all the possibilities of V and U being occupied, and you count, and you get this expression. And the important thing here, though, is that the two graphs were separated before, or actually, you don't really care that they were separated. The important thing is that before you added the edge, the two events that V and U occupied are independent of each other. Then you can do sort of this formula. And actually, for example, you can use this rule to see to get a standard recursive procedure for calculating the probability on trees that has been widely used. So what is this procedure? So suppose I write RT for this ratio at the root of the tree T, then you have a recursive formula in terms of the ratios at the children. So basically the way to see how you get it from this rule is that you start from the root being isolated, in which case you just have this ratio is just lambda, and then you add each subtree. So because in the tree there are no loops, you can keep continuing using this rule whenever you connect each subtree, and each subtree contributes this factor. Okay. Now the stopping rules for these procedures are sort of the trivial. If you get to a fixed vertex, then the ratio at the fixed vertex is infinity or 0, depending on whether it's occupied or unoccupied. Or you can also get to a leaf which is unfixed, and in which case, like I said already, this ratio is simply lambda. So this is the procedure for the tree, and I want to get something like that for the general graph. Namely, I want to express the probability that V is occupied as a function of the neighbors being occupied, possibly, hopefully in some smaller graph, but the main point is that in a general graph, when we do have loops, I cannot use this formula because there are dependencies between the neighbors. But sort of maybe like what you expect when you want to imitate the case of things being independent, you have to apply some conditioning. But the question is, what is the right condition? So now I'm moving on to describing a procedure for a general graph. So the first step is a conceptual step. So let's say that we start from the graph G and the vertex for which you want to calculate the probability of occupation. Then the first thing we do is split V to 1 degree vertices. So if the degree of V is D, we have D copies, each of them connecting to one neighbor. And another thing, sort of conceptual, that we think here is that since these vertices are really only 1/10 of a real vertex, we associate a smaller activity to them, just lambda to the power 1 over D. So sort of if V1 is occupied, it only adds a factor lambda to 1 over D. And now, simple observation is that the ratio of probabilities, what we want to calculate for V, is the same as the ratio between the probability that all these copies are occupied and all of them being unoccupied. Simply because in terms of the independent sets constraint, this is clearly the same. And in terms of weight, this is also the same. So what we want to calculate is actually this ratio. And now sort of what we gain from splitting this is sort of, you can think of this step as canceling the loops in some sense. Now we can sort of just isolate the contribution of each neighbor without having to worry about dependencies too much. But let me just continue. So we want to calculate this ratio, but now we can write it as a telescopic product. So we can write it as a product of D term, and in each step just change one of the copies from being unoccupied to being occupied. Okay? And now that since except at this vertex the configurations are the same in all the other copies, then we can just treat the configuration on the other copies as a condition. So we can think this for a specific term in this product, this ratio is simply the ratio of conditional probabilities of VI being occupied to not being occupied when we have the condition that the copies above it are fixed to being occupied and the copies below it are fixed to be unoccupied. So this is, again, I can just write it in the notation that I used before. So it's in the graph G prime, it's the ratio that VI is occupied to not occupied with this specific condition. And now I can go on and make a recursive step. And I'm now looking at a specific term in this product, so on a specific ratio. And now I can use the rule that I described before, because now this copy VI has only one edge connecting it to the rest of the graph, then clearly I can use this rule. So the ratio at VI is, again, simply given by this lambda 1 over d, the ratio when it's isolated, and then the contribution coming from its neighbor. So the contribution coming from the neighbor, I have to compute it when I erase this edge. So this is essentially this graph. Okay. So, and this gives me, this is where I get a recursive step. So if I plug it back in, so the ratio at V is well, if I take now the product of this D term, I get again lambda, and then a product of a contribution coming from each neighbor, which is but again, I have to put a different condition for each neighbor and look at a graph of this sort.
So you've managed to get recursion relations in something that's
Yeah.
not recursive.
Yeah.
I mean, that's really...
I mean, I will discuss that.
It's really surprising
Yes.
that it's possible to do that, right? I mean, what
Yeah, it is better than what I expected when I started to work on that, if that's the question.
I mean, I would have put money that, that you couldn't do that. What is wrong with my intuition?
So I think we'll come back to that in a second. I think there will be some explanation why it's not that strong. In what sense it's not that strong, but
because it just seems.
Yeah.
It seems
it
like.
starts to worry me because of norm. I mean, have you proved P with that?
No, so that's why. Okay, that's where I get to. That's what I'll get to in a second.
Okay.
Yeah.
Good. Okay.
So just to complete the proof that the two probabilities are the same, so again, I get like I said, I get a recursive step. By the way, this graph in which I have to compute the probability that the neighbor is occupied is indeed smaller in the sense that, I mean, even though I may even increase the number of vertices, I decrease the number of unfixed vertices by 1, because all the copies of V are either fixed or erased in this. So if I just go back maybe to this picture here. So all the copies of V here, so the smaller and larger ones are fixed, and the I itself is erased. So essentially V is erased from the graph. So this is a valid recursive definition, especially because whenever we get to a fixed vertex, that's a stopping rule. So back to saying why the two calculations give exactly the same result. So the recursive step is the same. It makes exactly the same calculation. Okay, if we plug in the same number coming from the children here and from the neighbors here, we will get the same result. So in order to complete the proof by induction, what I have to say that we get indeed the same numbers from the recursion. In order to do that, what I have to say, again, I will do that by induction. So I look at this graph and if this graph, when I do the translation that I described before to a tree, if I get this subtree, then I'm done by induction. And actually, this is exactly how I define the trees in order for this induction to work. And the way to see it is, okay, let's look at this subtree. What is this subtree? It's a tree of paths, this time starting at ui. And the only thing I have to remember is that I already visited v. So whenever I visit a copy of v again, I have to make it fixed to being occupied or unoccupied, depending if I come from a smaller or larger neighbor. But this is exactly what is going on here. It's essentially the tree of paths, and whenever I will visit v, this is v, it is fixed depending on whether I come from a smaller or larger neighbor.
So that's how you came up with
Yes, yes, yeah. Okay, so this essentially completes the proof that the ratio of v for g is the same as the ratio for the root of the tree. And here I did it without putting conditions on g, but it's easy to see that if I just put some vertex here, all you get is that this vertex is fixed to the same thing here. Okay, so now I'm sort of done with the proof of the main theorem, but I want to talk about the algorithm that I said that is coming up in this work, and it's essentially this recursive algorithm here, but notice that it's not really it's an algorithm for computing exactly everything exactly. The problem is that it's not an efficient algorithm because the running time of this algorithm is the size of this tree. And this is maybe exponential, actually in most graphs will be exponential in the size of the original graph because it's a tree of paths. Okay, so that's why it's still consistent with everything we know.
Oh, the distance to the boundary grows. In general,
Well, but you generate so many
Yeah.
different paths from
Yeah.
every way to
Yes.
come around every loop. And so, although, yes, you have given us the recursion relation,
Yes.
it is
Not an
it's
efficient one.
huge.
Yes.
That's kind of, but you're, yeah.
Yeah, but to solve the sort of the combinatorial problem that I described before, it's still valid because
Sure,
if you look at conditions here, the distances of what you get here is at least
But I
what they
guess
used to
my
be.
intuition was
Yes.
based on.
Yeah, on this being an efficient way of
Oh,
calculating.
and now, however, if you truncate the tree at some distance.
Yeah. Okay. So yeah. So you're already jumping to my next slide, actually. But so yeah. So it's reasonable that this algorithm is exponential if you do everything exactly, because otherwise it would solve an NP hard question. But what we can do, and this is what sort of Christian was starting to say, is sorry, yeah, this was part of the. If we only want an approximation algorithm, and if we know that we are in the subcritical regime where influences decay with distance on the tree, then actually we don't have to develop it all the way down. So basically we will run this algorithm with an additional parameter L, which tells us how many levels down the recursion do we want to continue. And actually maybe I do want to go back. So if you look at this formula, obviously if I plug in a lower or an upper bound on this value, I get a lower or an upper bound for the next step, and vice versa. So I can sort of propagate lower and upper bounds here. Sorry. So what I will do is the following. If I run this algorithm again with this parameter L that tells me to develop the recursion only L levels deep, is really to analyze it is the best way is to look at what is on the corresponding tree. So what I actually do is I calculate what happens on this tree, but when I get to level L, and if I get to still an unfixed vertex at level L, then instead of continuing further, I just say, well, I don't know what is the probability here, but it's certainly between 0 and 1. So I will take as a lower bound to be 0 and upper bound to be 1, and continue further. Now, what this means is, okay, so saying that the lower bound is 0 is just the same as calculating it with this side being unoccupied. And taking the upper bound to be 1 is just the same as calculating it with this side being occupied. And if I do the same for all sides at level L, then what I actually calculate, the two numbers that I calculate at the end for the root, is 1, the probability condition on everything that was unfixed being occupied. Again, everything at level L. And the other bound is just what happens on everything, condition on everything being unoccupied. So I get some interval, which the right answer is guaranteed to be in this interval, and this interval is just, the size of this interval is just the difference between the conditional probabilities condition on these two configurations. And if I'm at the subcritical regime, then I know that this goes exponentially fast to 0. Then I can set L appropriately.
It seems that you don't have a monotonicity if you have a mixture of occupied and
No, but I know that these are the two extremes.
why do they know that?
What?
Why are they big?
Why? Because, well, it's because it's a bipartite graph. So if you, so you can also look it from, you see it from the formula that I described, okay? So if you start from a lower bound here, you get an upper bound here, an upper bound here gives you a lower bound here, and okay, so.
But that's not wrong because you actually have a little occupied dot.
This one, but this one I'm not playing with it. This one is fixed.
So this sort of external boundary.
But given that these are fixed to these values, the maximizer and minimizer on the rest are all unoccupied and all occupied.
This is FKG.
Yes.
This is just.
It comes from the fact that this is a monotone. Yes, it's a
Long
monotone.
FKG, I
Yeah,
understand
it's
that. It's a conditional FKG.
Yeah.
No, I really understand.
Yeah.
That's, but it really is true.
Yeah. Okay, so and then if
Well, it's a form function.
But you don't need it.
You don't need it here.
yes, yeah, yeah.
Just do the function.
And just to finish the analysis, so if we do run it with the parameter L, then the running time is definitely bounded by some exponent in L. This is also where we get the dependence on delta in the exponent of the running time. And since we know that for subcritical activities on any tree, these things decay exponentially fast with L, the size of the interval shrinks exponentially fast, then what you get is that if you just want to estimate the probability that V is occupied, you get to a factor 1 plus epsilon. You need to run it in time polynomial in 1 over epsilon. Now, if you want to count the number of independent sets, you have to approximate this probability to something like 1 over n, and again, it depends on epsilon, so that's where you would get.
But what does it depend on the difference between lambda c?
Well, the thing is that the constant in this exponent will deteriorate as you approach the critical value.
Lambda over lambda c or something?
I'm not sure how that, but obviously this
I mean, look, it's probably going to
Yeah.
involve the correlation length,
yeah,
and the correlation length goes like lambda minus lambda c to the minus nu, and nu on the tree is 1/2, so
Huh.
it's probably going to go like lambda minus lambda. I mean, I would
Yeah.
bet that's going to go like lambda minus lambda c to the 1/2.
Correlation is on the trees.
No, but nu is 1/2.
Yeah,
I
but
mean,
is
you've
that
got-
correlation to point to plane or point to point or I mean, not clear.
anyway, he's right. It's going to
Yeah.
go lambda minus lambda c to something.
yeah. And okay, so this is the approximation algorithm. So let me just summarize. So we've seen a new.
This is PowerPoint.
No,
No, it's not PowerPoint.
no, it's Apple. Yeah,
Oh, it's Apple. Oh, yeah, of
Yes.
course it's Apple. I see. Okay.
yeah.
I thought that if you were supposed to have some design sensibility, then anyway, it's lovely. Go
By
on.
the way, you could run PowerPoint on Apple. I'm sure
Yeah.
that's almost
Yeah.
I'm sure that's just what he wants to do.
Okay. So we've seen a new tree representation that's valid for general graphs, and that proves the conjecture that the tree is the worst case in terms of this decay of correlation. And also it gives a new sort of tree-like algorithm for approximately counting all the way to the tree threshold. And we even got the improved bound for specific interesting examples. And I just want as a last slide to mention maybe some interesting open problems, maybe especially the first two. So So as you can probably see from the true representation that I gave here is actually, there's nothing specific about the hardcore model here, it's just the fact that there are only two spins.
So why do you need antiferromagnetic?
That's for the first part, that that sort of, it's not exact, the analog there is, the statement is slightly different, but the first part that I didn't do, in which that irregular trees are worse than regular trees, this kind of, if you translate that to what you need in the Ising model, that part is not true in the ferromagnetic. It's sort of strong mixing versus weak mixing. That's what I did here. Is the general claim is that if you have strong mixing on the tree, you also get strong mixing on a general graph. But to go from weak mixing to strong mixing, it's true that for antiferromagnetic models on a tree that weak mixing implies strong mixing, but for ferromagnetic it's not true. That's sort of. But in any case, there's an interesting question here of whether you can do something like that for systems with more than two spins, and especially for colorings, for example. Is the number of colors that are enough for the tree, are they enough for any graph? To get uniqueness on a tree, is that enough for
Well,
any?
but you know, when you have more than two spins, often you don't.
Yeah, it's
You don't
not no
have
necessarily
rotation,
monotone.
or
Yeah,
you
there's.
don't have, and I wonder if with this you couldn't, with this representation, you couldn't prove things
That are not true. Yeah.
You know, for like a
Yes.
three-state Hotz model or something like that. Whether you couldn't rule out first order phase
Yes.
transitions or something. So I would.
Yeah,
I mean, I was going to ask you this question,
Yes.
but the caveats that were going
Yeah.
through my head
Yeah.
before I was going to ask
Yeah.
it was, would it automatically lead to proofs of things that are not true?
Yeah. Oh, yeah. Maybe it probably needs also some kind of modification.
besides-
But yeah.
Maybe something else besides that, because you need some kind of correlation
Yes.
inequality.
But
You
it's.
have an alternate graph if you put a staggered magnetic field or your independent vector.
What kind of external field?
So
Staggered.
you make lambda different on the E.
Oh, you can have it, the lambdas don't have to be even uniform. All that you care is that they're less than the critical one. All of them are less than the critical one. Then it still works. Any graph, take any graph, and if you decrease any specific lambda for any vertex, it still works. As long as all of the activities, so suppose you have an assignment of activities. As long as the maximum activity is at most the critical one for the tree, then you have everything works. So this is sort of the first interesting question, and the second one is to also match the hardness result. So maybe lower the bound on lambda for which we know that the problem is hard even to approximate, and I mean, it would be really nice if the real threshold is this lambda c, and it could be. And if this is true, then it would sort of be what we always look for, this connection between computational complexity and phase transitions, to have a rigorous statement. Yeah, and the other two are just really, I think, more technicalities rather than interest, something deep.